The routes of nuclear decay, fission, and fusion going to be the topic of this lesson. And we're going to talk about 5 routes of nuclear decay, and that's alpha decay, beta decay, positron emission, electron capture, and gamma decay. And then we'll spend a little time talking about both fission and fusion, 2 nuclear processes that produce a ton of energy. Now, this lesson is part of my high school chemistry playlist. I'm releasing them weekly throughout the school year. So if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. All right, so we'll start off with these 5 spontaneous routes of nuclear decay. These are nuclear reactions that are common in a kind of a spontaneous fashion. And we'll see that some nuclear reactions are ones that we can cause. We usually will shoot like a beam of neutrons at some nuclear material and things of this sort to cause them to happen. But these are processes that'll happen often independent of that, but also sometimes happen in conjunction with that as well. And so you're going to want to get good at recognizing what is actually happening in each of these processes. You might have to predict what a product would look like after a particular nucleus undergoes one of these processes, and you want to know kind of what the net result is as well. So we'll start with alpha decay, and if you look at alpha decay, beta decay, positron emission, gamma decay, these are all examples of emission. So this could also be called alpha emission, this could be called beta emission. So positron emission already is called positron emission, and then gamma decay could also be called gamma emission. And when you're doing an emission, it means that a particle or ray is being emitted, and when it's being emitted, it means it's produced. It's a product of that nuclear process. So in this case, if we're doing alpha decay, it means that we are going to have an alpha particle as a product. So, and in this case, we're going to find out that alpha decay, this is the only one of these processes that the particle that's being either emitted, or in the case of electron capture, captured, has a mass number that is not 0. And so it turns out, what is the big, deal with alpha decay? Well, this allows a nucleus to reduce its mass number. And this is important. So we didn't talk about trends of radioactivity in this chapter, and we're not going to for a high school chemistry class, but we find out that heavy elements tend to be radioactive. In fact, all of the elements above atomic number 83 are all radioactive, every last one of them. And so it turns out, if the nucleus gets too big, it just becomes unstable and is likely to undergo nuclear decay, radioactive processes. And so it turns out one of the only, or in this case, the only way it has of reducing its actual mass number is if it does alpha decay. And so lots of heavy elements, it's pretty characteristic for them to undergo alpha decay, as we'll see. And so let's say we take uranium 238, and it's atomic number 92, and we say, hey, what would be the product of alpha decay of uranium 238? And you'd have to predict it. Well, you'd have to know that, okay, if you're looking for the product of alpha decay of uranium 238, then uranium 238 is reactant, but you'd also have to know that an alpha particle is on the product side of this process, and then you'd have some other mystery particle here as well. And you have to figure out, okay, what could that be? Now, you should know that when we're doing these spontaneous routes of nuclear decay, we often call the reactant nucleus the parent nucleus. We often call the product nucleus the daughter nucleus. So parents and daughters, kind of just the terminology used. And just like we learned how to balance nuclear reactions in the last lesson, we'll just fill in the blanks here. So in this case, with your 238 on the reactant side, we've got a total of 4 so far. We're going to need another 234 on the product side. And then for the atomic number, we've got a total of 92 on the reactant side. So far, we've got 2. We need another 90. So, and the atomic number always determines the element. So if you look on the periodic table at atomic number 90, that is thorium. And so thorium 234 would be one way to state this, would be our daughter nucleus from the alpha decay of uranium 238. Cool. And if you notice, mass number definitely has gone down, in this case down by 4. All right, so next on the list is beta decay, and I want to point out at your table on your handout, by the way, where I've got all these kind of categorized. The last column on the far right on that table tells you which nuclei are most likely to undergo these processes, and if you notice, all of the data in that column of the table is all grayed out, because it's not super important for you. In fact, I'm not going to give any real importance to it, but we can actually predict which nuclei are likely to undergo each of these processes, it turns out. But I'm not going to put that on you as a high school student. You're not likely to encounter this in any sort of high school class. So, but if you take a college course in the future or take the AP course in the future, you'll probably be on the hook for that. But I include it there. It's grayed out. Just keep in mind it's there only for your pleasure, in case you get curious, things of a sort, want to dive in a little deeper, but you're not on the hook for it in this lesson. All right. So beta decay is next, and a beta particle, you might recall, is the equivalent of an electron. And so beta decay, or beta emission, is where we're going to emit a beta particle, an electron. And so in this case, we're going to actually treat each of these reactions on uranium-238 as the parent and then predict the daughter nucleus. Now, uranium-238 is not actually likely to undergo all of these processes, it turns out, but for the purpose of this lesson, I'm going to ignore that. I just want you to be able to predict that daughter nucleus when required. So in this case, if we do the beta decay of uranium-238, what would be the lovely daughter nucleus? And once again, we'll just balance accordingly. And so in this case, for the mass number 238 equals 0 plus, we're still going to be 238. And then 92, if we're -1 here, this is going to have to be atomic number 93. And if we pull out our handy dandy periodic table here, I know you guys just all keep one within arm's reach as well. So atomic number 93, way down at the bottom here, is neptunium. So we'll stick that up there. Cool, and the daughter nucleus would therefore be neptunium-238. How would characterize that isotope? All right, positron emission is next. And again, you're not really going to find positrons too often on planet Earth or in this universe largely. In any kind of isolated way. But we are going to have a nuclear process here that is going to give off a positron. Now that positron's not going to exist for very long, it turns out, after it's emitted, because it's going to bump into an electron in all likelihood very quickly with a big burst of energy, and we track those big bursts of energy, kind of how we know this is going on. So if we did this, again, positron emission, and we did this for uranium-238, what would be the daughter nucleus? Well, in this case, we're giving off a positively charged electron. And so what do you got left? Well, again, it's still going to have a mass number of 238, but now, so it's just going to need an atomic number of 91. And we'll pull this guy out yet again. And if we look at atomic number 91 here, that is protactinium. So, and that is one that I remember very well. So, because believe it or not, I don't have the periodic table memorized. I just don't, because there's a periodic table everywhere. I've got one on my bookshelf. I've got one over on the wall over here that you can't see. I've got shirts with it on there. I've seen it on socks. I've seen it on credit cards. I've seen it on tattoos. So they're everywhere, and you're probably going to have an access to one anywhere you want to go, especially if you got access to the internet in some way, shape, or form. You'll have one. So I don't have it memorized, and it's probably smarter to not memorize it, right? So, but I had students quiz me on this way back in my early days of teaching, and they said, "Chad, what's atomic number 91?" And I said, "I don't know." And they looked at me stunned. So, and then I explained to them that I was smarter for not knowing. Yeah, so if you bought that, there you go. All right, but that's protactinium. All right, let's take a look at electron capture here. So electron capture is the one that's not an emission. So in an electron capture process, you actually have one of the core electrons being sucked into the nucleus of an atom. So not the most common event in the world, but it does on rare occasion happen. And when that electron gets sucked into the nucleus, it actually becomes part of the nucleus, and it combines, as we'll find out, with a proton to form a neutron. So as part of this nuclear decay process. But being a capture, it's not that you're producing an electron in this process, you're actually consuming one. It's a reactant instead. And so in this case, if we did electron capture with uranium-238, we'd be adding an electron, and most commonly you'll see it used E, but it could still be used as beta here. So, and in this case now, what are we going to end up with? Well, we're still going to have a mass number of 238. Let's make that 3 look a little better. So in this case, 92 and -1 is 91, so it's going to be atomic number 91, and it's still going to be protactinium. And so it turns out 2 of these processes accomplish the exact same thing, and probably worth noting that is positron emission and electron capture. So it turns out that some of the heavier elements would be more likely to do electron capture, some of the lighter ones, positron emission, but it accomplishes the same thing. But again, who's likely to do it? You're not on the hook for that. All right, gamma decay is our last one here, and gamma decay is super duper duper high energy electromagnetic radiation here, and because it's gamma emission, it's on the product side. And so notice then, if we just got zeros here, well, then I'm still going to need 238 here, and I'm still going to need 92 for an atomic number, and that's still uranium. And so it turns out gamma decay is the only one of these processes where your parent nucleus and your daughter nucleus are the same nucleus. It doesn't change the identity of our element. Not true for all the rest here. So, but totally true for gamma decay. So it turns out oftentimes when you're doing certain nuclear reactions, it leaves you with a very high energy, unstable nucleus in an attempt to just get a little more stable. Like you might think of it as the equivalent of like being in an excited state like we saw with electrons. So when you have a nucleus that, you know, complete some sort of nuclear process, it might end up in some high energy state. And to drop down to a lower energy state, it will emit energy, just like we saw electrons give off light. So usually, you know, either in the ultraviolet or visible or infrared area of the spectrum. But now we're going to see light being given off, but in the super high energy gamma ray region of the spectrum. But your parent and your daughter nucleus are one and the same. Cool, so let's go back and look at this for a second. So I just want to look at these middle three right here for a second, and so we can characterize what's actually being accomplished a little more than what we've said so far. So if we go back to positron emission and electron capture, so electron capture, so you can kind of think of a neutron in the nucleus. So look at that neutron. Neutron has zero charge, and it weighs a little tiny bit more than a proton. So if you take a proton with a +1 charge and combine it with an electron with a -1 charge, if you were actually able to combine them, you'd end up with something that's neutral that weighs just a teeny bit more than a proton, i.e. a neutron. And that's actually what's going on here. So, you know, not required as part of the course by any stretch. So, but all these lovely subatomic particles are made of quarks. And so when you combine them, you might just get a rearranging of the quarks to turn them into different subatomic particles. And that's as much as I really wanted to say about this, so that just didn't seem so weird. So, but in this case, when you suck in one of these core electrons, it combines with a proton to turn it into a neutron. And so you could say that the net process here again is to convert a proton into a neutron. That's what both of these ultimately accomplish. And you can kind of see that here. Our mass number is not changing in either one of these processes. And so the total number of protons and neutrons not changing, but we can definitely see that our number of protons has gone from 92 down to 91. And so if the number of protons went down, well, then the number of neutrons would have to go up by 1 to keep that mass number the same, i.e. we've converted a proton into a neutron. That's what both positron emission and electron capture accomplish. That's definitely worth knowing. All right, if we look at beta decay, it's actually the exact opposite. We're actually going to be converting a neutron into a proton instead. And so when you emit, when you emit an electron, so right here, kind of think again of that neutron as being the combination of a proton and an electron. That's what a neutron is. And when you emit out the electron, all that's left behind in the nucleus is that proton. And so you had a neutron, which you can kind of think of as the equivalent of a proton and electron combined. It's not technically completely true, but that's how we're going to think about it. And that neutron, it's going to eject out its beta particle, its electron, leaving behind a proton in the nucleus. And so this converts a neutron into a proton. And again, that's also worth knowing. Now, if we had to take this a little further, we'd find out that having a certain ratio of neutrons and protons is ideal. And if you have too many neutrons and not enough protons, well, this would be a great way to go, beta decay. But if you had too many protons and not enough neutrons, well, then one of these would be a great way to go. But again, that's going to be beyond the scope of what we study here in this particular lesson and in this class in general. Cool. So these are your 5 routes of spontaneous nuclear decay. So you definitely want to be able to predict daughter nuclei given parent nuclei. You're going to want to know what they accomplish as well. So now we're going to talk about fission and fusion. And if you look at those words, fission and fusion, fission is the splitting apart. And that's exactly what's going on here in this nuclear process. You've got a very large nucleus being split apart into 2 or more smaller nuclei. Whereas fusion is the exact opposite. Now you're going to be taking 2 smaller nuclei and combining them together into a larger nuclei. And I say 2, it might be more. So same kind of thing here. So I've given you an example of fission, and here I've given you an example of fusion. So but you're going to want to know where these occur as well. Now, when we talk about nuclear fission, so if you have a large nuclei splitting apart, this is what's going on with your heavy elements. So when you think of like uranium and plutonium and things of a sort, they're likely to undergo nuclear fission. So, and these are typically induced by neutron bombardment. So you've got a neutron as a reactant here. So, and this is what's going on in your typical nuclear reactors and in certain nuclear bombs as well. So that are based on like uranium and plutonium, things of a sort. And so uranium-235, it turns out, is your good fuel. So unfortunately, it is present in a very small amount with uranium-238 in a much larger amount. But you can, again, as we discussed earlier, we can separate those by centrifugation to get the uranium-235 enriched, we say. So, but you got to mine the uranium, now you've got to purify it with centrifugation, and all this is pretty expensive. We're going to find out that if we had a good way of doing fusion, it'd be a lot cheaper, because a lot of times the fuel for fusion is going to end up being hydrogen, and there's lots of it as part of H2O in the water around the world. So, fission, much more costly to get the fuel for it, but it's one we can do. Fusion, we're going to have some problems with, as we'll see. All right, so nuclear fission, induced by neutron bombardment. If you look specifically at the nuclear fission of uranium-235 here, what's interesting is that you're going to produce, you're going to consume one neutron, but you're going to produce 3 more. Now, this is not the only decay route that is at uranium-235's disposal here, it turns out. There are some others, but they all produce multiple neutrons as well. And so it turns out when you start doing nuclear fission with uranium, it produces 2 to 3 additional neutrons. And so this can be a problem. Like, you could look at this as a good thing, or it could be a big problem depending on how you look at it. So if you try to get this process going by bombarding it with some neutrons, all of a sudden now you've done this once, and it produces, say, 3 more neutrons all on its own. Those 3 neutrons go and find 3 more uranium nuclei and cause them to undergo nuclear fission, and those 3 nuclei now produce 9 more neutrons, and it just keeps getting multiplicative. And so the problem is, if this goes too fast, it's not going to stop, and you're going to get a fission meltdown. You're going to have a problem. Well, so there's a couple different ways we can prevent this from happening then, and one is just don't have too large a piece of uranium-235 around. So, and it turns out, though, that if you've got too large a piece of uranium-235, when it reaches what we call a critical mass, well, then you can't stop this process, and a chain reaction occurs. So, and it turns out this is how a nuclear fission bomb is kind of built. What they do is they take pieces of uranium-235 and line kind of the outside of a bomb, little piece here, all around the edges of a bomb. And when that bomb goes off, you actually have these charges that detonate that force all those pieces to the center together to form this critical mass. So that's kind of what's going on there. Now, in a nuclear reactor, we don't want that critical mass to ever be reached. We don't want, that sort of problem. So what we do is we actually, have these uranium fissionable rods, let's say, and we put them out and expose them to a beam of neutrons, and we speed up the reaction. And when it starts going too fast, we just retract them back into a sheath that protects them from the neutrons to kind of slow it down and stuff like that. And, once upon a time, one of these got stuck and it couldn't retract, and that was a big problem back in the day. And now they have all sorts of redundant systems to keep that from ever happening again and stuff. So it turns out nuclear energy, regardless of what you might hear, is one of the safer types of energy. It just is, in principle, seems kind of scary to our psychology. Cool, but produces tons of energy. So with not so much fuel, if you compare it to like going through gasoline or something like that, if you take your entire gas tank full of gas, let's say you got a 10 gallons in your Corolla or something like that. So that 10 gallons might weigh like, 70, 80 pounds, depending on the density of gas and stuff. So let's say 70 pounds. And 70 pounds of gasoline can drive your car like 400 or 500 miles or something like that. Well, 70 pounds of uranium-235 could accomplish a whole lot more than that. 70 pounds of uranium-235 could power a large city for a significant period of time. Like, I'm going to guess that it's on the order of years. That is maybe not years, but a very long time. Let's just put it that way. So days and days and days at the very least, weeks, maybe even months. So, but a very long time. So and the big thing is that we're not doing a chemical reaction now, we're doing a nuclear reaction. And it turns out when you look at any nuclear reaction, it doesn't matter if it's nuclear decay or fission or fusion, you're going to find that your products always weigh less than your reactants. And this is not immediately obvious because if you look at the mass numbers, they're always balanced. 235 plus 1 is 236. 142 plus 91 plus 3 of these plus 3 more is also 236. You're like, Chad, the mass numbers are balanced. They are. But again, these are all rounded to the nearest whole number. So, but if you take and get the exact masses out to like 5 or 6 decimal places of all the species involved here, you're going to find out that these products total out to be just a teeny bit smaller than these reactants. Because in any nuclear reaction like this, you're having mass being converted into energy. And when a little bit of mass gets converted into energy, a little bit of mass gets converted into a whole lot of energy. And so that's going to be the important thing here. And that's why these have such a much bigger payload than a typical chemical reaction, these nuclear reactions. All right, so that's fission. Let's talk about fusion for a minute. So fusion, your fuel is now very small nuclei being combined to form larger nuclei. So problem is that for fusion currently, from what we understand, and I might date this video by doing this because there's some good research going on, but currently fusion only occurs at really, really high temperatures. Now when I say really high temperatures, I mean like millions of degrees centigrade. So super, super high temperatures. Well, where do you find temperatures like this hot enough for this to happen? Well, at the center of a star, like the sun. That's where it happens. Not even on the outskirts of the sun, at the very center. And at the center of our sun, that's what's going on. We got nuclear fusion going on, and this is just one example. So, but here we've got, turns out heavy hydrogen. These are both forms of heavy hydrogen. We call this one deuterium, this one tritium. They just have extra neutrons. So they themselves are produced by nuclear fusion going on in the sun. So, but in this particular reaction, it's where the helium in the sun gets produced. And it turns out our sun is made up of like 70% regular hydrogen and another, I don't know, 27% helium and a few percent of heavier elements. And so it is successive fusion from bigger and bigger pieces of fuel that make some of the trace elements. And that's where we think, all the elements in our solar system and throughout the galaxies were produced in some of these nuclear fusion results in various stars. And when those stars, say, go supernova, it spreads it out throughout, the solar system and all that kind of stuff. All right, so this nuclear fusion has nice, convenient fuel. Again, if we could do this, we got plenty of hydrogen all over the planet in the form of water, right? And so the problem is that, if I want to do nuclear fusion, I've got to have I got to heat it up first to millions of degrees, and then it could do, nuclear fusion. Well, to get it to millions of degrees, that would be very costly for one. It costs a lot of money to heat things up. So, but two, what container do I put this all in that won't melt at millions of degrees? So there's some issues here with trying to do this, and there's a lot of research going on with like modular fusion reactors that might fit in, say, the back of a pickup or something like this. But the reality is it's not there just yet at the time I filmed this, and I hope before the end of my lifetime to say, hey, look, we're doing nuclear fusion and my video's out of date. That would be fantastic. So, but it would be great because we'd have a cheap source of energy. And it would be plentiful, and plentiful, cheap energy is really one of the big keys to pulling people out of poverty, globally. So super important from where I stand. And this would be a great route for it to occur if we can do this cheaply and safely. Now, in addition to being at the center of stars, though, there is one other place where we do see nuclear fusion, and that is H-bombs. So not all nuclear bombs are nuclear fission bombs. An H-bomb is actually a nuclear fusion bomb. So problem is that, so you got this lovely lighter fuel of hydrogen and stuff like this. So for this nuclear fusion bomb, problem is this bomb is not going to go off until it reaches millions of degrees centigrade. Well, how do you get your bomb to go off then if you have to heat it up first? Well, what they do is they attach a nuclear fission bomb to this nuclear fusion bomb. And the nuclear fission bomb goes off, because that can happen at like room temp and stuff like that. And that nuclear fusion bomb going off heats up the nuclear fission bomb going off heats up the nuclear fusion bomb to where it goes off. And so it's kind of like the nuclear fission bomb acts as a detonator for the nuclear fusion bomb. And so if your detonator is a nuclear bomb, you are a big bomb, so to speak. So, and that's kind of what's going on here with a fusion bomb. So at the center of stars, and then unfortunately only in H-bombs. We don't have a way to control the energy being produced in a fusion or a fusion reactor as of yet. But like I said, lots of research being done. Hopefully that is on the horizon. Cool, and these are just some of the characteristics of both fission and fusion that you're on the hook for. We're going to look at how to calculate the energy involved in these kind of processes in the next lesson. Now, if you found this lesson helpful, would you consider giving me a like and a share? Best thing you can do to make sure that other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on nuclear chemistry, check out my premium course on chadsprep.com.